So let me once again welcome you all to this course on testability of VLSI. So today's is just an introduction class. So we won't be taking major concepts today. We'll just see an overall why this course is important. Okay, so that is the aim of today's lecture. Okay, in 1994, okay, Professor Thomas Nicely he reported a bug in Pentium, right? There was a problem with the restoring division algorithm, and then that error, by the time he found out that error, 1 million unit ships, a million units have already been shipped from the factory to the consumers. And then around $450 million was the cost recurred by for recalling of these chips by the Intel. Okay, and then it was decided by all microprocessor manufacturing companies that they would have more stringent formal verification included in their process. Okay, so that is where the focus on testing came. Right, so you have to ensure that whatever product is going out of your company has to be 100%. Right, fault free. Okay, so that was the aim. Now let me just explain these two difference between what is a verification and what is a testing. Now essentially verification is before fabrication and testing is after fabrication. Okay.
After fabrication.
So verification is correctness of the design, okay, performed by simulation, hardware emulation, or formal methods. Okay, so here also it is performed prior to manufacturing, responsible for quality of design, and no limit on number of test points and vectors. Okay, so all these things are done before the manufacturing. Okay, the thing is, suppose you have an 64 bit adder into 64 bit adder. Okay, so does verification involve 2 to the power of 64 plus 64, that is those many combinations? Do you have to check, right? Is that possible? It may not be possible, right? So there is a science to it. Okay, and verification also has to be done judiciously. Okay, so verification prior to manufacturing also doesn't mean that you take every vector and try to find out every possible combination. Okay, so there is verification also has to be done judiciously. So I will touch upon that in the subsequent slides. Okay, so I don't think verification means an 100% right a check of all the logical if like 100% verification of each and every combination of input. It doesn't happen that way. Okay, because that is going to be very time consuming, right? The one advantage out here in verification is there is no limit on number of test points, right? So in between also any wire or net, because it is just a simulation, you can take out the output, right? You can plot the output or see the output or measure the currents in any net, any node, right? That is possible. There is no restriction there, right? But whereas in testing is verifies the correctness of the manufactured hardware. Okay, so for that once this chip is fabricated, before that only you during the design of the chip you need to generate the test pattern. Okay, so it and manually it won't be possible, so there has to be some software, and that is what is the focus area of this course. Okay, so firstly we should know what are the kind of faults which will be there. Okay, how to model that, and what are the test vectors which will identify those faults, and is it possible that one test vector will find multiple faults, or for each fault will you keep going and finding out what is the vector? So that optimization, okay, through software, that is going to be the focus area of this course, right? Now another thing is during testing, okay, we are not going to verify what is, you give a certain kind of input and we are trying to find, suppose no, it's an adder. I am not going to find out during testing. I am giving 2 and 2 input, whether I am getting 4, okay, in an adder. That is not the purpose of testing. The purpose of testing is that has been done in verification, and we assume that if it is fabricated correctly, the chip will work. Okay, so in testing we are only seeing that whatever has been designed, has it got properly fabricated. Okay, so the focus is during fabrication, has there been a broken line somewhere, has there a fault, like stuck at 0 has got induced or stuck at 1 has got induced. Okay, so during testing we are not checking the functionality of the chip. Testing is essentially the functionality of the chip is ascertained during verification, and we assume that since, and during verification we also do process variation, temperature variation and things like that. So all those things are already taken care of here, right? So in testing we just test whether it has been correctly fabricated or not. Okay, so we don't do exhaustive post fabrication check with regards to the functionality. Okay, we do testing whether it has been correctly. So that is majority of the testing is done that. Okay, that is the, so testing, you require electrical test applies to the hardware, okay, on the manufactured device, responsible for quality of devices. Now during testing you will find that there is limited number of test points. Okay, because physically you have to measure the output voltages and you have to give input and signals. So unlike in verification where you have full freedom of seeing the signals anywhere in the circuit, so that freedom is not available here. Now although verification is done, then what is the requirement of tester? Because during manufacturing there could be a process, and especially so for in nanoscale devices. Okay, as you are shrinking the device, the probability of defects are more. So that is the reason, if you see for space applications and for aviation applications and all, some of them still use because there is no space constraint there that much, right? And but reliability is a very critical issue for space applications and for aviation applications and all, for military grade systems. There still 180 nanometer is used, because that is so the it is very matured technology, okay, over the period of time now, and the number of defects that would occur during fabrication would be minimal, right? But for non-critical applications like our mobiles and desktops and all, that is the place where we keep pushing nanoscale devices, because they operate faster and have higher performance, but then they're not very critical. So if something fails, it is not going to critically affect anybody. So that is the reason. So now you could have defects in PCB, environment, temperature, humidity, vibration, power supply fluctuations, wear and tear. So these are external factors, everything post your verification. So this testing take care of all these issues. Right, so this is the ASIC design flow. So you have the specifications first. From the basic specifications, we will have an architecture, right? So we will decide what is the architecture to be implemented, and then that architecture will be converted into an RTL, right? So you have design architecture could be in C, okay, C++ or something like that. RTL, you have a Verilog code here, right? So once you write a Verilog code, you could run that code and verify the results, correct? So all your tools which are there, most of the tools which are there, you can write a Verilog code and check the functionality at this level itself first. Okay, after having done that, then you go for logic synthesis. So what is the when you come to logic synthesis, what happens? this is just a code which is written. Now, when I say logic synthesis, the tool will try to implement that with the gates. Okay, now so the tool needs to be given a library file. Okay, for all these gates, generally it is from the manufacturer. Okay, some manufacturer provides the technology files, like LT Spice. We use 180 nanometer technology, right? So similarly, here in the logic synthesis, say 180 nanometer gate models will be given. Okay, not the transistor model, the gate models and or. So based on the code which we have written, it is going to synthesize this logic. Right now, each gate, right, it is going to be technology specific, and in the logic synthesis also so like for an OR gate also, from the fab lab, he might give you several kinds of OR gates, okay, which is low power, fast, and things like that. And also a certain circuit can be implemented in multiple ways, and that can ensure that the gate sizes also, right, a bigger current carrying capacity, or gate could be there, lesser current carrying capacity or gate can be there, which will make it faster or slower, or high power, low power. So all those variations is possible, right? And hence, when we do the logic synthesis, generally a window would pop up something like this, which would ask, okay, the tool would ask you what is the figure of merit you are trying to optimize, okay, whether it is speed, power. So that goal also requires to be set up. Okay, so now you have specifications, design architecture at C++ level or something. Then you have a Verilog code, and that Verilog code which will be synthesized into the gates, and the gates are technology specific, and when during synthesis, prior to the synthesis, you need to also specify what are your goals in terms of whether you want to optimize power, performance, or area. Okay, so that kind of thing. Once that is synthesized, you would want to this particular RTL code may not have the provision for testing. So you need to include certain modules which will enable testing, right? So and then you go back to the RTL design, again do a verification and come back, because first once you are done the logic synthesis and you have run a simulation, you are confident, okay, this system works. Now you introduce the testing right things also. So once you do that, again you you finish off with this particular loop where you have inserted your extra modules which will enable testing. Then there would be an incremental synthesis. That means again, right, you have implemented this in so you are in the synthesis, there will be something, some incremental means some extra gates and all will be required to be synthesized, right, because of this. Okay, and then see till here it is all only functional, pure functional check. Okay, that means you give A, B, C, whether you are getting A plus B plus C. Okay, that kind of simulation is happening till here. Then you do the floor planning. Okay, placement and routing. Okay, once you have done, again this is also automated these days. So once you have done that, then you do the timing analysis. Okay, because once you do the floor planning, then okay, obviously the clock signals which are being routed, the data signal which are being routed, there could be necessity of some buffers, because you have an suppose you have an right, and you have an some chip like this here, so the clock requires to be distributed to, so right, once you do the placement and routing, there could be some buffers which will be required, so that clock adequate driving capacity is available for all these clocks. So these buffers can introduce a little bit of delay. So all those things we will come to know only after the floor planning, placement and routing, and then you do the timing analysis. Okay, so there is a static timing analysis as well as dynamic timing analysis. So STA is very important aspect there is one full lecture on this on STA we will learn in the advanced VLSI course. Okay. After when it passes that, then you have the automatic test pattern generation. Okay. This is for the focus of this course. Okay, we will learn this. Okay, because then you are sending it for fabrication. So before fabrication you need to generate a test pattern. So we generate a test pattern, then you send the tape out. Generally you send the GDS2 file to the fab lab. Okay, GDS2 is nothing but an once you make your layout and everything is ready, that circuit, you don't send the layout and the schematic to the fab lab. In fact, that layout will be in the final layout. Okay, you should have the pins, input output pins, ESD ring, everything. Okay, you have to select. The fab lab will give you various kinds of chips. Okay, it could be a square chip with 48 pins or a package. Okay, so different packages are available, right? So I think those packages also we'll learn in VLSI course. So so once your everything is done, you will have to select that package also. So including those package and everything, so the layout of the package will be available, which will and then you place all the ESD rings and the input output pins, and then you generate the GDS2. This will be sent to the fab lab. So based on this, they will make all the masks which are required for various CMOS process, and it gets manufactured, and then you do the testing. So this is how the ASIC design flow looks like. Right. So like this, the formal verification is nothing but checks which we do prior to fabrication. So if you see when you are making an algorithm, if you do a check there itself, and if you are able to find a fault, okay, it would take minimum time. But if you skip this level, and if there is a fault, and for the same fault to be identified at an RTL level, it will take more time. And if the same fault, because this takes more time for a circuit to get to do the exhaustive checking. And now if you go for a transistor level checking, it is going to take even more time. So it is very, very important that as we move in the ASIC flow from top to bottom, okay, some kind of formal checking should be done at each level, okay, so that the time is saved. So no point making everything and implementing it at transistor level and do the checking, and if there is a problem, it takes so much of a time and you go back there. So we will come to RTL implementation only after all the formal verification at the system level is done. Similarly, once only the RTL level checks are done, only then we go to the transistor level checking. Right. So when we do the transistor level checking, it will do everything. Right now, the currents which are available in the transistors, whether it's adequate, rise time, fall time, all those issues. In RTL, it will be just a gate level implementation. Right. So this is how the formal verification sequence is there. Again, formal verification can be further classified as model checking and equivalence checking and theorem proving. So these are the two important things. Combinational equivalence checking or sequential equivalence checking. So we'll talk about that in the next slide. So formal verification is mostly two types. One is formal equivalence and formal property checking. Okay, equivalence checking will be done at every level, right? So like you make an RTL, right, versus the pre-routed netlist. That is here, though you between the architecture and RTL, so you can't do any equivalence. Right, once you do an RTL, from here the equivalence will start. Right, once you have done RTL and you have done logical synthesis, right? So whatever you have written code here and what has been synthesized, and they have to be the same, right? So whether it is the same or not, you need to do a check. Okay, and then you do the floor planning, and routing has been done, right? So whether what has been routed and what you have done these two also have to be like the gate level which was synthesized, and after the floor planning, okay, these two circuits have to be the same. So there is an at every level such kind of equivalence checks needs to be done. So that is what it does. So RTL to pre-routed, pre-routed pre-routed means before routing. Okay, routing versus post routing, and netlist versus echo netlist. Okay, function. That means what this means is, once you have a netlist out here, right, then you have included DFT scanning, and you might want to change it a little bit, okay, for performance enhance or for the testing purpose. But then finally this functionality and this functionality should not change, right? Suppose you are doing A plus B plus C out here, and then you insert some testing things here, but here again it should be A plus B plus C only. Functionality should not change. Okay, so that is what this says. Okay, functional engineering change order, this should not happen, because from the initial netlist there will be lot of optimization which would happen at this level, right, at this level. So that should not change the functionality. So that so you have in cadence conformal or synapses formality and all, so which does these kind of okay checks, okay, whether when you are moving from one level to other. So RTL to gate level netlist conversion is done in Genus, and this is from Cadence. So then again that synthesized net can be imported into Cadence Composer. Okay, so you can write a Verilog code, and then that can be the net. You can obtain that code, right, netlist in the Genus, and then you can use Cadence Composer. So this is. So our focus of this course is not for a formal verification. Just in an introduction class, I want you to just know about how formal verification is done, so that when we do testing, in the back of the mind we know that okay, now what we are going to do in testing is just check of fabrication issues, and most of the logical issues have already been resolved during formal verification, right? Okay, this is like a formal equivalence checking, RTL and pre-routed. So you see, this is the code which is written, this is the circuit. So these two have to be matched. Okay, so this is the kind of equivalence checking which will be done by the tool, whether these are matching. So automatically it will generate this. Okay, there is no problem with that, but there is a provision for you to do changes here also. Okay, manually, because once it is generated, you might want okay, this is not better, let me your target is maybe speed of operation, and then although you have given speed, your goal as a high speed, but once this tool has picked up this particular module, you can see from your experience that this particular mux, I would want to replace it with a faster, so I'll replace it with a faster. Okay, this was one initially generated automatically. Now you have done some optimization here. After doing that, again you would want to match, right, whether this and this, after the changes which you have done, does it match, or has the functionality got disturbed? So that kind of check can be done in the tool, right? Similarly in Cadence also, you can you have an schematic, then you will make an layout, right? So you will draw a layout on that, but then the functionality cannot change. So you will run an LVS check. LVS check is nothing but a layout versus schematic check. Okay, then one it will say okay, 0 cells have mismatches, 0 devices mismatches, pin mismatches. So in this layout, and between the layout and the schematic, if there is some mismatch, okay, those errors will be displayed on after the check is run, and then accordingly. So it is like pre-routed netlist versus post-routed netlist. So these all they come in the formal equivalence checking. Okay, now how does the tool do that, right? So how is that, and tool analyze that this is okay. Now we saw that right, this. Okay, so in the background, what does the tool do? what the tool does is, suppose this is f is equal to a plus b plus c. Okay, it will convert this into a binary decision making chart. Okay, now log a, right? If I put a equal to 0, what would it happen? Then it will become c plus bc. So a equal to c, then I go to b, and then if I put b is equal to 0, right? No, if I put a is equal to 0, this term becomes 0. It is only bc. Then I go to b, and then if b is equal to 0, the output is 0. So I write it as 0, right? But if b is equal to 1, then it depends on c. So I go to c, and if c is equal to 0, I come back to 0, or c is equal to 1, the output is 1, right? So again I take the next combination, a equal to 1. If I take a is equal to 1, it will be c plus bc. So I go to c plus bc is what? I am writing a equal to 1. Oh, sorry, already in the pen mode, right? And if I put a equal to 1, this will become c plus bc. So this is nothing but if I take c, it is just c, right? So a equal to 1, I come to c, and then c is equal to 0, or c is equal to 0 is 0, c is equal to 1. So this gets mapped like this. Now if I try to map this, right, this I have written in c. Now if I try to write an Verilog code, this is the code, right? If I try to map this, again I will get the same thing, right? If I try to map this circuit, okay, this again comes to the same thing. If I map this circuit, this also comes to the same circuit. What is this? If you see here, this is what? AB plus BC, right? If I take AC plus BC. If I take C common, it will be C into A plus B, right? That is what this. So these two circuits are same, right? So how does the tool know this is same, this is same? It will convert it into a binary decision making table. It will convert this into a binary decision table, and see whether ultimately for all the combinations, if I am getting f to be the same, right, that means it is that the circuit is same. Okay, so this is how the tool runs in the background. Okay, so all this equivalence checking is generally done on BDD basis. Okay, binary decision making tables. Okay, so is it okay till here? Anybody has got any doubts? No? Okay. Okay. So now there are two types of simulations. Okay, one is known as exhaustive. Okay, so and then one is selective. So obviously exhaustive checking is not possible at the system level, but then when you have a project, then small modules may be designed by individual groups. Okay, so those groups for that particular module you might want to do and 100% verification, exhaustive checking, but at system level we can't do, right? So when you move to a slightly higher level where you have so many modules which are interconnected, then there is no option but to do selective testing. So that is where formal property checking or the model checking comes. Okay, so this formal or model checking is not fully automated. Okay, unlike when we are going for testing algorithms, automatic test pattern generation, it is totally softwares and algorithms are available, right? Formal verification, it is only partly automated because every circuit, every design is different. Okay, so what kind of test vectors are good enough to tell me that the system will work? Okay, that is very, very subjective in nature, right? Person to person it differs. So these days the best engineers are deployed for formal checking. Okay, because this requires a lot of creativity, right? It can save time and effort and find the faults with minimum of time is a crucial factor. right? So you can't afford to spend 6 months doing testing, so because that will delay the entire fabrication process, right? So within a given limited time, how best can you do that? Okay, so that is what a test engineer or a formal checking task is all about. Okay, so this is it requires a lot of creative thinking. Okay, so that is what is done. So these are the tools which are system verilog, cadence, jasper and all. So they are the kind of tools which are used for formal verification, right? So actually I didn't find very good examples to drive this point about formal verification, but I picked up some examples which is not very good enough, but still it will give you some idea about what formal verification is. Okay, so you will find a few more in the textbooks. Okay, but let me discuss this particular. It will give a rough idea about what formal property checking is all about, right? Suppose I have a module here. Okay, it is an arbiter. Okay, what is an arbiter? We will transistor level implement of arbiter is there in the advanced VLSI design course. Okay, so I have two requests which are coming, R0 and R1. Okay, this is the reset pin. So when the reset goes, when the reset goes, it is a reset dash n. So if the reset is 0, then both of them will be 0. Okay, if the reset, this is so this is a dash n indicates that it is a negative logic. Okay, so when the reset is 1, then I have depending on the request, there are two guys are asking some request. Okay, so two interrupt signals are coming. One of them will be granted, okay, high. You understand what is an arbiter? You have a microprocessor. So suppose there are several chaps wanting services from the microprocessor. For example, your mic, your mouse, your key, some inputs you are giving from mic, some inputs you are giving from your keyboard and all. So the whatever input you are giving, this microprocessor has to take on that task and produce the results. So all of them simultaneously can't communicate with the microprocessor. So in between you will have an arbiter. Okay, arbiter is only you could say you can call it as a priority interrupt controller. Okay, so you have all the requests from external devices coming to this arbiter, and he will tell the microprocessor to take on task of which guy. Okay, now suppose R0 I want to give higher priority. So I designed a block which says if R0 is high, then obviously this will go high, right? If R0 and R1 both are high, then this will go high, and this will go high, grant 1 will go high only if this is not there and this is there. Okay, this is the second priority interrupt. Okay, so only so, and then this will go high. So I write a code for that. Okay, so it says if reset is 0, right? If reset is 0, so this is not equivalent for. So if reset is 0, that is if reset is not high, then you put an output as 0 0. Okay, so this is, so reset is 0 means this will be 0 0. Otherwise, okay, if this is this is high, then you put this as high and this as 0, right? Else, okay, that means if this is not there, then if this request is high, then you put this as high. Okay, so that is how you write a code. This is a block now. Now suppose you have written this code. Now if I have to do a functional check of it, now if I have to do an exhaustive check, okay, so how many inputs are there? Input this. So how many test vectors, minimum test vectors are required? Can anybody say?
8.
8. Okay, only 8 are required if this is a combinational circuit, correct? If it is a combinational circuit, but if it is a sequential circuit, right, then the number of test vector cases will in a sequential circuit, if RO has come earlier, if this has come earlier, okay, and when these are high, when the clock is high, then the reset comes, what happens, is it edge triggered? So many issues are there, right? So you can see that just for a combinational circuit, 8 is required. For a sequential circuit with another clock coming, even the way these test patterns are coming, that also will start making more, if you have to do an exhaustive checking, those many more conditions requires to be checked. Okay, so say when you are actually designing this module, okay, that particular team may have the time to do the exhaustive checking, but at a system level I may not have that much time to do the exhaustive checking. Okay, so I might do a simple small check, okay, a formal, that is known as formal checking. And what is formal checking? So I'll write an assertion code. Okay, here I just check 3 or 4 properties. Okay, first is during the positive edge of the clock, if reset, so now if reset is 0, then you assign this as 0 0. Otherwise you have to check for this. Otherwise you put an error message like this. Okay, failed so and so. Okay, in the second check, okay, if request is otherwise, if this is not there, then you check the next property, request is 0. Okay, if request 0 is 1, then grant 0 has to be high and this grant 1 has to be 0, right? And you write the third property and the fourth property. There only, if you see, the entire functioning of this block can be identified as 4 properties. Okay, 4 main properties. R0 is 0, G0 is 0 in the next cycle. So these 4 properties you can define. So those properties can be mapped as an assertion file, and then accordingly you make a test bench where, like, initially everything is 0, then you give a negative edge of the clock, reset you give it as 1, right? Then request equivalent as 1. First you give reset as 0 and check whether the outputs are 0 0. In the next condition you put reset as 1, request as 1, and request 0 as 1 and check the output. Then you just switch the request 1 to 0, right? There is one more condition. Then you request 1 is to be put to 1. Then again you put both of them to 0. So both of them are 0 0. That is also a condition which is defined here, that if there is no request, then grant 1 should be high. Okay, so that is a default condition which has been stipulated. So you put for that particular condition also. So now if you see 5 6 conditions, you just run, and this will give you this is the kind of formal checking which is done here. Okay, no, so this is a very crude example. Okay, now the thing is, this is a small test. It is obviously not I can't say if this is passed, this circuit, okay, is 100%, no, it would work. Okay, so not, but major functionality has been checked, and that is where the formal property checking comes in. Okay, small teams can do 100% verification, but at system level, okay, I have to understand what purpose this is supposed to do, and accordingly generate a program which won't take time and do a formal checking. Okay, so this is all very specific to the circuits. Okay, so you don't have to remember all these things. Okay, this is just an introduction course, so I'm just giving an essence of what formal verification is all about. Okay, so we will talk about testing, where everything is streamlined and proper algorithm is there. So don't get bogged down by these examples. This is just to give you an idea. Okay, similarly, if I have an modulo 3 counter, what is modulo 3 counter? It is just a 2-bit counter. Initially it is 0 0 0 1 1 0. It won't go to 3. Okay, because it is modulo 3. Modulo 3 means there are only 3 states, and then again it comes back to 0, right? So this is the counter which you have designed. This is a state which is not there. So how to do a formal verification of this? Okay, right? If you want to do an proper checking, then you will have to take this pattern, this pattern, this pattern, right? And then do that. Instead of that, if I take the first pattern and 0 0, right, and see that the next pattern is not equal to 0, and after 3 clock cycles, if I am getting back again 0 0, okay, you can fairly assume that this is the counter which is working perfectly. You don't have to verify if the second one is 0 1 or 0 2 at the system level. Okay, it's a modulo 3 counter. You can fairly assume, okay, 0 0 is the first count, and next is not a 0 0, right? That means because after 3, if you just take only one condition, okay, 0 0, and after the 3 clocks, if you take 0 0, you never know it is continuously remaining at 0 0 or not. Okay, so that will be too optimistic. Okay, you might be missing some information, right? So but instead of that, if you are checking for 0 0, right, and then you are seeing in the next clock it is a non-zero thing, and then you are checking that after 3 clocks only this is becoming 0 0. So in a microprocessor, if you keep loading that data, there is a 0 flag, right, that would come up. So you can see that only, right? So same thing, this is just a modulo 3 counter. It could be a modulo 65 counter or modulo 120 counter, right? In those things, every bit you need not ascertain whether it is following the sequence coming or not, because, right, if you have designed a, say, 113 bit counter, right? So because you have, say, so many timer circuits, right, where you fill in some data, right, when you want you want some time delay, specific time delays, you fill in some data, and the counter will start from that data to come to 0, right? So you want to verify whether this particular design is proper or not, right? So you want to check whether, okay, so what you just don't have to check whether it is following those. So you just trigger a signal at 0 0, and then you keep monitoring the because it will decrement, right? Like, you understand what are timers in microprocessors, right? There will be a timer circuit. Like suppose so suppose the microprocessor has received one input from somewhere, right? From some one interrupt controller, and now it has done
Sir,
that some processing into one core. Yes, tell me.
yeah, like a timer in the sense something like watchdog timer
Yeah,
circuit.
watch type timer circuit, correct?
Okay,
So it
okay,
will be there
yes.
in where you load some data, right, and then it will come to 0. Okay, and
Yes, sir.
meanwhile it will do some other function. Okay, because say suppose it is given some signal to some display, or where you want that, then you need to come back to that program only after certain time. Okay, so meanwhile, so you will activate some timer. So in those kind of applications, you don't have to actually go through each and every data. So what I mean to say is, in formal verification, it is all very subjective in nature, and the person who is designing these formal verification codes need to understand what is the requirement at the system level. Okay, so that is all about formal verification. Then you could do a static verification or a similar functional verification. Also, this is static verification is at an is against some predefined rules, right? Whether this particular node has to be at VDD or ground, that kind of very very basic, and then followed by that functional. Okay, so even in the functional simulation, okay, during verification process, initial verification process, time delays are not considered of interconnects and all. So this will be done during the static timing analysis, which is done post routing. Okay, so this is this we will talk about detail about static timing analysis, because there will be flip flops and things like that in between, right? So the data needs to be presented to the flip flop at a time known as setup time before the arrival of the clock itself. Okay, because along with the clock, if you give data, then it may not capture the exact data. Okay, similarly, there is something known as hold time. Hold time is nothing but you have given the clock, but this data cannot change immediately. It's a positive edge triggered clock. So you may say the moment the positive edge has come, this data is captured. Now I can change the data. No, there is something known as hold time. So for that, there is some definite time required for this data to be captured. Okay, that is known as hold time. So is there any violation which is happening, okay, at the desired frequency of operation? So those kind of analysis will be done in the timing analysis. So this aspect will be covered in detail in the other course. Okay. Now this is VLSI again, same thing. You have design, verification, and a fabrication, prototype test. Again, the feedback is given to the, if there are some errors. Okay, if there could be a debug during verification itself, that is incorporated. After prototype test also, right? Here you need to do a functional check also, right? Maybe, right? So so some amount of functional check also has to be done, okay, during the prototyping also. Then in the mass production, generally after the mass production is done, it is just the you may do very limited functional checking, but you will do an pure testing only here in these stages. Okay, so that is it about. Now testing is like there can be different results. This is, you have done a testing, a good IC pass, if it passes the test, it is a true pass, right? And defective IC passes a test, okay, this could be an issue. Okay, so that means your test scheme is not proper. Okay, so you have, so your whatever test you make, it has to cover all the faults, possible faults. Okay, and that is what we are going to learn in this course, right? And now again the same thing is when you are making an automatic test pattern generator. Okay, if it is going to fail good ICs also, okay, then you will unnecessarily, your yield will be lesser. Okay, so this is again not desirable. So this is not desirable, this is not desirable, right? But if it is a defective and it is a failing test, okay, so this is what is we required. So these two blocks are what is required. So we have to minimize these two conditions in our testing, right? So let's cover 2-3 slides and then we'll take a break. Okay. Then there are several types of testing. One is known as characterization. Okay, characterization is nothing but verification. What we learned till now. Okay, so all these are verifications. So while we do verifications, okay, we do AC analysis, we do DC analysis. This is all simulation based before the fabrication. We can do probing of internal nodes, okay, because that is possible in simulation. We can do for all PVT corners. Okay, some books also call post fabrication silicon debug, like basic DA test, like VOL, VOL TP, not full functional check, just checking the VOL, VOH and things like that. Post fabrication, that also in certain books, and it is referred to as characterization. Okay, then we have production testing. This is what is the main goal of our course. Okay, where so to do this you need to generate test patterns. Okay, okay, that is what we are going to learn here. Okay, now here, like we are not doing functional checks, but we are only trying to find out the faults in fabrication. Okay, that is production testing. Here burn-in, here we do a functional check. Okay, here we can do some bit of functional testing. A burn is nothing but an accelerated life test. Okay, so once the chip is fabricated, the prototype chip is fabricated, we will run it on a test bench, right, for a long period of time. Okay, now but obviously if you want to say that this is this would work for 2 years, you will not wait for 2 years, right? So you might want to do it, you might want to do an accelerated live test. Okay, how can you do an accelerated live test? Maybe you can do it at an increased temperature, right? So or other at a faster frequency, or things like that. So you can impose more stringent conditions, and then because no, if you are saying, okay, my chip has to work for 2 years, I will not wait for 2 years. Okay, so there has to be some scheme for accelerated live test also. Accelerated live test just means that no, you don't wait for the entire duration, but some way within a short span of period, you judge whether it is going to last for 2 years by making the test little more stringent. Okay, and then you have an incoming an inspection. This is not for VLSI chip testing, but at a system level where there are multiple chips, right? Then when you have those chips coming in, then you might want to do some kind of checks on each of those modules, and then put together on a PCB and do a system wise checks. So these are some of the types of testing. Then you have this wafer sort of pull. Once the wafer is made, right, on the wafer there will be several dies, right? On a single wafer there could be hundreds of dies. Okay, each all the dies may be of this doing the same function, right? So replica. So you can we have to have a test pattern available, and a hardware which will test all those things. Okay, so it is done before the packaging on the wafer itself. Okay, so the die itself is checked. On the wafer there are several dies, so you are not cutting and taking out this die and making an packaging with pins, right? On the wafer itself, on the wafer itself you are doing this check. Okay, because this will be a waste of time. This also has to be done later on during prototype testing. Okay, so you understand what is being done here? Wafer testing, right? On the wafer you have several dies, right? You will have several dies. So is it okay?
Yes, sir.
What this is? Okay, so without cutting and taking out these individual dies from the wafer, on the wafer only. So these kind of test benches are available, right? So all these chips, entire chips, dies. Now on the chip there could be hundreds of dies. All will be checked up. Okay, so you need to have. So this test pattern generation is what we are going to learn. Okay, then there is some parametric test. Okay, which includes a short test, open test, leakage, and all things. This also can be done. Okay, and then functional test. Okay, this is for the proper logic. So some limited amount of functional test can be done post fabrication, not an exhaustive check. Like there are other, like this is another test bench which is available from advanced test. Okay, this machine itself is made up of 350 nanometer VLSI chips. It can simultaneously check these many channels. Okay, so 1024 chips can be simultaneously checked. Okay, so those many proofs are there. The speed is there, drive bus. These are some of the specifications of this test bench. I'm just giving you, all the kind of test benches which are available. Then we have one more, a few more available from the NI. Okay, NI instruments. So they also have got some softwares which can run, on which these can be run, and the test programs can be run, and there will be some interface units through which you can give signals to these dies, and then take the output and do the measurements. So these are some of the test benches. Okay, this is known as smooth plot. What it does is, like for on a wafer there are several dies, right? So I do change a frequency here. So I am going towards higher frequency here, and I change the VDD. How many dies have failed? So these are the dies which are failing. Okay, So I make, so when I do on a wafer checking, there are several dies available. So I make these kinds of plots. Okay, so these dies are no, these many dies are failing, or for these conditions it is failing. So I know, okay, so this is my good operation area. So if I go at high frequencies, or if I increase the VDD, this is failing. Okay, this is two dimensional. Or I can have an three-dimensional plots like this. Okay, here it is VDD, here one is frequency, one is VCC Q. VCC Q stands for the supply voltage we give for the input output pads, okay, to prevent EMC interference. So for all these three, if you vary what is the area where the chips fail. So once this fabrication is done in all when the testing is done on the wafer, depending on the results, these test machines, whatever is there, okay, most of them they give these kind of results, final results, with which you can analyze, okay, where to operate my these kind of results are also available. Okay, doing in the nominal voltages, that is okay once you do that. Okay, after doing it at the nominal voltage, you can also change these parameters and get these kind of plots also. As engineers, we tend to neglect an cost aspect, right? But because we are more worried about the technical issues. But ultimately, for any company to survive in the long run, okay, cost is a very, very important aspect. So let's just discuss for 5-10 minutes some of these cost versus quality level trade-offs. Okay, so a fixed cost is those costs that are that don't change. For example, the machinery, right? And once you have procured this machinery, that so as you keep increasing the production, right, and whether you produce one item or you produce 1,000 item, that cost is fixed, because that is the initial investment. Say infrastructure, you have that you have made a hangar and where you have installed all these machines, and they all come under the fixed. Variable cost is okay, that is for each quantity you require certain raw materials, right? So as you keep increasing, if you want to increase the production, these things also needs to increase. Even the manpower also can be considered as a variable cost, because if you have to produce say 100 items, you might require 10 people, and if you have to scale up to 1,000, you might have to employ 100 people. So they are all variable costs. Okay, so that is variable. Total cost is sum of this fixed cost and variable cost. Okay, and the average cost is this total cost divided by the number of units which is produced. Okay, so now if you see here this graph, this is the fixed cost, right? And this is the total cost which is going high, and this is the variable cost. So total cost is sum total of this, right? So as you keep increasing, this is an example for miles, that is for an automobile, if it is running, right? So you will assume that right, as you keep driving more and more, okay, the average cost would keep coming down, right? So because what happens is the fixed cost is going to get divided over them. So similarly, if you are going to produce the if you have a machine of say a few lakhs, and if you are going to produce more and more ICs, that investment which you have done as part of your fixed cost, okay, that keeps getting divided, okay, per chip, right? So actually this graph has to come down, but in practice that doesn't come down. After a certain amount, okay, it will go up, because as you keep increasing your production by few millions and all, there will be breakdowns and issues with your fixed costs also. They might require maintenance, replacements. So it is observed that after a certain time, even the this curve goes up, actually doesn't come down here. Okay, so for a given fixed cost and a recurring cost, okay, for a certain, till you attain a certain amount of production value, this will come down, and subsequently this is known as the aging factor. Okay, as it starts getting aging, more and more problems do come up with the machines. and things like that. So this can go up. Okay, so this is one. Now average product, okay, product is known as this is the output and this is the input. Okay, so output by input. So obviously you will have to map these in a single unit. Okay, either you convert everything into rupees or dollars, and then you take them, because okay, so all of them, all the products and the inputs may not be directly in terms of dollars, it may not be available, right? So you have to find some ways and measures to make an equivalent input and an equivalent output. Okay, and then and marginal product is change of this small change in input, what would be the change in the output. So that is marginal product, and our aim should be to maximize this, okay, average product. So you take an this has to be maximized. So if you differentiate it with respect to x, so when these two things are equal, okay, when the average product is equal to the marginal product, and that is the situation which is best suited for us, right? So that is shown here in a graph also. Now here, if you see here, what happens is your input is increasing, right? But after a certain time, your output may not increase proportionately. Okay, so this can become stagnant out here. Okay, because there could be several restrictions which would come here, right? Maybe you have increased your raw materials, but your machine is no more able to produce those many results, or there could be limitations in the manpower. So so if you keep increasing the output, okay, a single output, single input, okay, so this might increase, but after a certain time it could get stagnated, right? And depending on, because there might be time might be a restriction, right? You have a machine, you have a thing, but each thing will require certain amount of time, right? And then if you so, and hence if you increase the input also, there could be like you are producing, you have increased your production, but your testing requires certain amount of time. So you can do maximum testing of 100 units. So from going from 1 to 100, if you are increasing the input raw material, you can increase the production. But if you are further increasing, there is a bottleneck there of testing, so it can get saturated. So depending on that, okay, so when you plot these two lines, it will intersect here. So this is the optimal condition. So you have to see that is known as maximizing the technological efficiency. Okay, that is one. So this is again, right, this is known as a bell curve. Okay, so this bell curve we saw here, right? This is known as the bell curve, real curve. Okay, as you keep increasing this, the fixed cost will keep getting divided among the output, and subsequently because of other factors, the fixed cost also, there will be an increase, some replenishment of the actual initially invested fixed cost items will be required, and hence this curve is, so this is known as a bell curve. So so this is the bell curves. Okay, average cost with no fixed, this is with a fixed, and this is the place where increasing fixed cost. So you will find that some this is as you keep increasing the fixed cost, this curve keeps going up. So this is the optimum place, maximum economic efficiency, we call that, right? Okay, this is known as law of diminishing returns. That is, if one input of a production is increasing, keeping the other inputs, then the output may increase, eventually reaching to a point beyond which increasing the input will cause progressively lesser. So that is what, if you keep increasing only one input, you will reach some bottleneck. Okay, and because of which you can further not increase the output. Okay, this again we discussed earlier. So there is another rule which says that increasing scale returns to scale, that when you're increasing the scale, okay, there could be like suppose I have an input, okay, 1, right? So I am getting an output of 10. Okay, now I increase the input to 2, so I might get an output of 25. Okay, this happens before the onset of this saturation. In this region it can happen. Okay, this is not linear if you see here. So this is very steep. So that can happen because of this. Why that is that? Suppose I have one. This is generally the case. If I have one manpower, if I increase it to 2, right? So it is possible that some kind of a technical knowledge sharing is happening between these two guys, right? Similarly, if I have if I am having say a bigger wafer, right? If I am going to instead of a small wafer, I am going for a bigger wafer, right? Double the size of this wafer, right? So in this case, say these are the just give me 30 seconds. क्लास चल रहा है बोलो आधे घंटे में खत्म होगा क्लास हाँ ठीक है आधे घंटे बाद करो okay. So this is a wafer, say of an 10 inch. Okay, this is a 20 inch, right? In the 10 inch, I might have 100 wafers, and 10 wafers in the corner are getting wasted. Now I have increased my input. Okay, I have doubled it. I have taken a 20-inch wafer. Okay, so in the 20-inch wafer, it is possible that here also only in the edges only 10 dies are faulty, and instead of getting 200 I might get 300 also, because only the faults might be only in the outside ring, right? So here also only it might be in the outside ring, right? So instead of 10 ideally here 20 faults should be there, but the circumference here and here might be so that it's instead of only 15 faults are there, 15 faulty dies are observed, and instead of 200 I am getting 300 better chips. Okay, so that is what it says. Okay, so this phenomena generally happens only in this area, right? And after that it is going to get hit this saturation level. Okay, this starts getting dominated. Law of diminishing returns. So initially in the long run diminishing return prevails. In the earlier, if you increase the scale slightly, there could be an increased productivity. Okay, so that may not be linear, it could be an exponential growth of productivity can be there. Okay, so that is then benefit to cost analysis. You can do these also. This is annual benefits and total cost, right? So this also they need not be directly in dollars or rupees. So the benefits like for example for buying a car, benefit could be convenience of transport. Okay, so that needs to be that is a benefit. So that needs to be converted into cost. Similarly, if I talk about a silicon wafer, okay, not necessarily the cost, the total cost of this wafer, okay, is important. Okay, because by probably manufacturing this wafer, I am getting a greater hold of the market, and a successful chip which I am fabricating might give me more business from other sources, right? So obviously, that is also a benefit, right? Suppose I am making a chip for an automobile, specific automobile, say the lidar of an automobile. I am making a chip, right? So the benefit of making the if I just say okay, I am spending 1 rupee and getting 100 rupees, so 99 is my profit or my benefit. That need not be the case actually, because by making this particular chip, probably for the company, I am going to get a more automobile related chip tasks, right? So that kind of benefit also. So when we do benefit cost analysis, now all those things needs to be taken into consideration. Okay, Then there is something known as rule of 10. All these things are from your textbook. Okay, if you're interested, you could read through all these things. Rule of 10 means like when you are doing an suppose you're making a chip. Okay, if you are able to catch a fault during formal verification, it is good. If you are not able to do that, and if you are trying to do it at the testing level, that it will cost you 10 times. Okay, that much more time and effort. And if you are not able to do that during testing, then at the PCB level, if you are trying to get that fault, then you will get again 10 times more effort, cost, everything. So it is better that as you move from your design cycle towards fabrication, your test has to be covering have a large fault coverage. Okay, so because any fault which goes undetected, okay, will have 10 times the effect, 10 times of that much more effort, and loss can happen as you move towards implementation the next stage. Okay, that is what the rule of 10 says, right? And then there is something known as yield. Okay, yield is if you have a wafer, you have so many dies here. So the total number of dies which are fault free. Okay, so fault free by total dies. Okay, so that is known as yield. Okay, now generally towards the edge only, most of the faults would happen during fabrication towards the edge. It would not be like this is very low occurrence. Okay, unless there is some specific design issue. Okay, generally if you have taken care of the DRC rules and things like that, then these kind of defects don't occur. Okay, but towards the edge of the wafer, you can expect some faults. Okay, this is how yield looks like. So now testing actually doesn't improve the yield. Okay, what testing does is it will diagnose, okay, if there is an issue, and in some fault tolerant designs, okay, you may have the provision of repair. Like if you have made a microprocessor or a chip, like if you have made an say multiplier that has got so many modules, right? What if one module has become faulty, right? Will you discard the entire chip, or in the design itself, can I have a fault tolerant design in these multiple modules? If one module is faulty, can I have instead of fabricating 100 small adders which together form a multiplier, can I have say 102 or 103 such adders there in the chip, and am I able to replace one of them after testing if I find that okay, one adder is faulty? Is there a provision? So there are some fault tolerant designs also. So let's see towards the end of the course, if I have some time, maybe one or examples I will discuss, but otherwise that can happen. Okay, otherwise generally it is only diagnosis. Okay, and from the diagnosis, you go back to your design table and try to minimize the defects. Okay, you have to analyze why it has failed. So was there a problem in your layout? Why it has got why that fault has occurred during fabrication? Is it because of defective material, or your layout issues where you have not catered enough space between the wires? Okay, or you have not catered for adequate thickness of the wire, that during test it has got burnt off. So all those things can be analyzed post your testing, right? So now there this definition which we are going to use, these two words, defects and faults, we are going to use throughout this course. So let me clarify what is a defect and what is a fault. Okay, defect is a physical imperfection in the processed wafer. Okay, that means a short or a open, right, or an open, all these things are defects. Or like if your transistor is manufactured increased VT because there is an problem with an oxide, or decreased VT, all those things are defects. What is fault? fault is an Boolean malfunctions. Okay, like stuck at zero fault. That means this particular net is permanently stuck to zero, or stuck at one fault. Okay, that means this particular net is continuously VDD is available there, or one of the faults could be bridging fault. That means there are two nets, but they have got shorted. Okay, so that is known as bridging faults. Okay, so these are the faults. So in our course, okay, we are not about worried about the defects. Okay, finally the defects are going to appear as faults. Okay, so we will detect these faults. Okay, so our focus will be fault detection. Okay, so that is the difference between a defect and a fault. Okay, now defects are measured, okay, as defects per million. Okay, generally for an IC, a defect per million of less than 200 is acceptable, and defect greater than 1000 is not acceptable. Okay, this is a very generalized statement. Okay, so for different chips, these figures might vary. Okay, there could be some critical chips which might want a DPM of below 10 also. Okay, so this is just a generalized statement. Okay, just a rough idea. Okay, now what is a system DPM is? In a system you could have multiple chips, right? So now suppose if a system has 10 chips and you have a DPM of 1000, that means 1000 defective problems in 1000 chips are defective out of 1,000,000. Then if you in the system, if there are 10 chips, then the system DPM will become 1000 into 10, that is 10,000 per million. Okay, that comes out to be 1%. Okay, that means if 1,000,000 system is there, then 10,000 will be defective. So this is a very large figure. So you see here, this 1000 is not a good figure, right? So here we have taken 1000, so that is why that. So now we have an something known as defect level. This is a figure of merit. Okay, which is means that a fraction of the bad IC passing the test, or test which is escaping. So this we have to keep as minimum as possible. So your testing methodology should have ideally DL to be 0. Okay, so if it is not 0, then that means there is an issue. So can you calculate the DM? Can you predict what would be your DM? So there are Brown and Williams. He has proposed one formula to calculate DL, which is 1 minus y to the power of 1 minus f c. Okay, here y stands for yield. Okay, so yield is number of good chips divided by number of total chips, and FC denotes fault coverage. That means out of the total faults during your testing, okay, how many faults can be detected? Certain faults cannot be detected. Okay, so this is FC, means fault coverage. Okay, how much can you do? How much of the faults can be covered? Now suppose you are you can do 100% fault coverage. Okay, if that is the case, 1 minus 1 will become 0, right? So y to the power of 0 is 1, so this is 0. Okay, that means if you are doing an 100% fault coverage, that means it is okay, DL is 0, you get a good. Now otherwise, the other option is, if your yield is good, that is you have got 100% yield, that means all the chips are coming being fabricated, okay, is good, that is yield is 1, right? In that case also DL is 0. Okay, now where do you get this figure of yield L? Why? That comes from the manufacturing. Okay, so every manufacturing technology will say that, okay, I am you have given me the design, okay, but my yield is say 90%. That means 10% of my chips will be faulty. He will say, the lab will say, right? In that case, now if I have to keep DL minimum, what do I have to do? Anybody? Say if the yield is poor, then how can I
Increase
compensate?
FC.
Yeah, I have to increase FC. right? If the yield is very, very high, so the company is claiming that 99% I am giving good yield, okay? So 99.99%, whatever design you give, okay, I will fabricate it like that, okay? So that confidence the Fab Lab is giving you, then you may not want to put in that much of effort in your, because some amount of DL is permitted, so you may not want to do an exhaustive fault coverage, because this is a very, very time consuming, and it requires a lot of resources. As we keep studying further, we'll understand that, right? So the amount of effort which we need to put, okay, to minimize FC, that depends on the yield, which is figure which is provided by the Fab Lab, okay. So there is a small derivation also here. It is not important for the derivation is not important, but these equations you might want to remember for your quiz and things like that, okay. So here this I have just put this derivation. I have taken I think from this link I have taken this derivation. So where it says ki, okay, this is fault coverage. D is the total fault. T is the total faults, out of which D is detected. D is the detected. So fault coverage will become D by T, right? And Q is the fault occurrence. Okay, the probability of fault occurrence. Okay, so if it is if there is no fault, the probability is 1 minus Q. Okay, this is fault probability. So 1 minus Q is that there is no fault, and there are T such things. So you multiply it by T. So this is going to give me the yield. So fraction of good ICs passing the test, okay, will be 1 minus Q into T minus T D, because D are the ones which are detected. So fraction of, so this becomes T minus D, right? So this gets so you take out T and you get this, right? And then a fraction of bad ICs passing the test will be 1 minus. So you don't have to remember this derivations, but through these steps you can understand where this has come from. Okay. Now the assumption made here is this is binomial distribution. That means the fault occurring Q is binomial distribution here. In this case, okay, it doesn't cater for that there could be faults which are more faults which could be there in the edges. Okay, this particular model assumes that the fault is placed all over the wafer in a binomial distribution format. Okay, but that need not be the case. So a more precise a better model has been provided by Agarwal. Again, you don't have to remember these derivations and all, just the formula would be good enough. Here he takes into consideration that these faults are localized mostly. Okay, here is showing it in the center of the chip, but it will be more or less localized towards the edges. Okay. So you have another factor of n also, which is average number of defects on a bad die. Okay, so that means there is a possibility that on a single die multiple faults are there. Not that each fault will be in each different die. Right. So this is very slightly pessimistic, because all the faults are equally divided over all the wafers. Here it takes into consideration that if you try to put these three faults in three different places as a binomial distribution, the thing is you will get an probably too pessimistic result, right? But this takes into consideration that there could be multiple faults within the die, and that is generally the case in towards these edges. Okay, so that aspect is also 10. Again, this n. Okay, now these data have to come from the Fab Lab. Okay, so once n comes from the experiment. Okay, once you have fabricated and you have done the experimented, right, and the yield also comes from the Fab Lab only, right? N comes from experiment means multiple. Once you have done this multiple times fabrications, then you know these faults are clustered now over this. So this also essentially this also has to come from the Fab Lab only. Okay, yield may not be specific to an die, whereas n could be specific to an die and a particular circuit. Okay, so that is how. So this takes into consideration that also. So this is again right. It takes into Poisson's distribution. Okay, instead of a binomial distribution. So again, this is not important for you. So we just covered only the basic things. So the takeaway from all these lectures is now a few of these things which test economics we have discussed towards the end of the class. They could be useful for your quiz and maybe small questions for your midsem also. But otherwise, we just understood the what is a formal verification. Although it is this particular course is not focused on formal verification. I just introduce you to what is formal verification. Then we discuss what is important is why testing is required, right? This. So now from the next class onwards, we'll focus on these aspects. Okay, so meet you next week. Okay, and towards the end of it, I think I have given the references. So this particular, the first class is essentially from your textbook only, right? But this is one set of video lectures. You could go through this. This is the textbook. In the next class, I will give you one more reference of another series of lectures, NPTEL lectures, which are also very good. You could refer to those also if you have certain doubts. Okay, so we'll stop it.